All right, welcome to the week 2 live session on the course NPTEL NOC24 EE-143 Semiconductor Devices and Circuits. Since there are not many students, let's wait for a couple of minutes more and then we can start. Fine, I guess I'll start. I've got 2 students. I'll be starting. Please try to join in time. Okay, again, the guidelines. You may go over through them. In case you have any query, you can just raise your hand or you can just type in the chat window. Uh, Please ensure that your microphones are muted, especially when you don't intend to speak. And I would appreciate your cooperation to make this session an interactive one. So I would especially encourage you all to keep pen and paper handy along with, a calculator. So the session recording link and the lecture notes, they will be duly shared by the NPTEL course team. Okay, so the prerequisites of this live interactive session include the following topics that were taught in the last week. It was excursion in solid state physics, wherein we learned formation of bands. We went through chronic penny model, electrons and holes, effective mass, crystals, uh, and many more such topics, right? And I'm assuming that all of you that are joining this session or watching this when it is in the recorded form, you all must have attempted the assignment 2 first yourself. Now, a brief recap of the topics again. Uh, the last week's lectures, it started with the band formation, right? And then we, just a second, why is it not? It's visible, right? Can anyone just check if I'm audible and it's visible? I just need these 2 confirmations. You can either just chat. Okay, fine. Thank you. So yeah, in chronic penny model, we considered a periodic potential in 1D crystal, right? Wherein we had some approximations. We went through a detailed, I would say, a treatment, right? I'm sure you would have seen the detailed lecture. Then we saw types of crystals like monocrystalline, polycrystalline, uh, and the rest. We also saw primitive unit cell, the elementary topics, primitive unit cell, and the types of unit cell like BCC, FCC, and end-centered, and etc. Then we also, I mean, went through Bragg's law of diffraction, and then we went through the concept of Wigner seed cell. Uh, we understood the reciprocal lattice space, and we were familiar with the concept of Brillouin zone, right? Now, let's try to solve problems that are based on these concepts. The first one, we'll be starting with the easy ones. The first one is what are the number of the lattice points per unit cell in a body-centered cubic lattice? I would hope that majority of you would answer this one. And please try to be interactive. It's up to you. You can either type in the chat or you can just unmute and let me know the answer. Okay, 2. Fine. Anyone else who wants to attempt it? This is pretty straightforward, right? 2. Okay. We got 2 answers for the option 2, D. Again 2. Okay, fine. I got 3 responses. It's fine. So what is a body-centered cubic lattice, right? In a body-centered cubic lattice, we have atoms at the 8 corners, right? And there is, you know, atom that is, I mean, that the unit cell covers, right? This atom, I'm talking about this one, right? Apart from these 8 ones that are present in the primitive unit cell, this is the one extra atom that is present in the BCC, right? So what are the number of the lattice points that I would have per unit cell in a BCC lattice? The corner atoms, they contribute to 1 by 8 contribution, right? And there are 8 such atoms. So it's 1 by 8 times 8, right? Plus 1, this one, right? So this is 1 plus 1 and that is 2. So we'll go with option 2, which all of you pointed out. So now another simple one. Number of lattice points per unit cell in a face-centered cubic lattice is. Please attempt this as well. 4, 4. 2 options pointing to 4. Anyone else who wants to go with option B or has other opinion? Anyone? Fine. So what is face-centered cubic lattice first, right? In a face-centered cubic lattice, in addition to the primitive unit cell, what we have is at the each face we have an atom, right? I mean, 2 unit cell. See, there would be, wait, I'll just rub it off. There would be an adjacent unit cell, right? Like this. The atom lying on the face is shared by 2 unit cells, right? So the contribution for 1 unit cell would be half, right? And there are 6 faces in the cube. So we'll have half times 6 contribution arising from the ones that are present on the faces of the cube, right? And in addition to that, we have the 1 by 8 contribution on the corners, and there are 8 corners. 1 by 8 into 8 plus 1 by 2 into 6, right? Which is 1 plus 3, that is 4. And 2 of the students had already gone with this option. So now let's move forward. Let's increase the difficulty level slightly. So gallium arsenide has a zinc blende crystal structure, right, which is equivalent to a face-centered cubic lattice point with 2 atoms per lattice point, right? You have to assume that this A, the lattice spacing, is 5.65 angstroms, okay? And the question is how many number of atoms per uh, CC are there in the gallium arsenide? Just work it out. Okay, so let me help you out. See, it is a zinc blend crystal structure, right? Which is equivalent to an FCC with two atoms per lattice point. Okay, fine. So what are the number of gallium arsenide atoms per unit cell? We just saw, right? For FCC, it was 4, right? You all, I mean, two of you said it's 4, and we worked it out as well, right? So it should be, see, this is what I'm trying to ask you all. Number of gallium arsenide atoms per unit cell. What is this? Let's move step by step. If you cannot answer the whole question, just answer this much. How many gallium arsenide atoms should be per unit cell if we know that it takes a zinc blend structure, right? Which is equivalent to an FCC with 2 atoms per lattice point. How many lattice points are present in FCC? 4. So 2 atoms per lattice point. So how many gallium arsenide atoms should be present per unit cell? Attempt it. 8. Correct. Right? Simple. 4 times 2, 2, right? Which is 8. So we have 8 gallium arsenide atoms per unit cell. Now it's given that A, the lattice spacing constant, right? A, that is 5.65 angstrom, right? So work it out. How many number of atoms per cubic cell are there in the gallium arsenide? What is the volume of the cube? Volume of the cube is A cube, right? And A is 5.65 angstrom. So work it out. Ideally, you should have a calculator in front of you because only then you would be able to work these out. Fine, take this as an exercise, okay? This is simple. So see, once you compute the volume of the cube, then the question, that is number of atoms per cubic cell, that is this, uh, it would be 8 into 10, I mean, yeah, just work it out. It should be 4.435 into 10 to the power 22 centimeter. Yeah, fine. Just work it out. You should get this number. Once you verify it, just type that yes, verified. I'll wait meanwhile. Fine. So let's move to the next one. Okay. You have to assume that the electrons in an n-doped crystalline silicon, they suffer scattering, right? Only due to lattice vibration and the interaction with impurity ions, right? Two scatterings. One, the lattice vibration, and the other is the impurity ion scattering. Okay, now the question is, at an extremely low temperature region, mobility, how does mobility change with increase in temperature? Should it become zero? Should it decrease with the increase in the temperature? Should it remain constant, or should it increase with the increase in the temperature? Okay, let's take it step by step. At extremely low temperature region, which of the scattering would it be dominant? Would it be lattice vibration due to the lattice vibration, or would it be the interaction with the impurity ions? Okay, since no one answered, I'll answer it myself. So at low temperature region, the lattice vibration will be mostly suppressed, right? And the dominant scattering would be due to the impurity ions. Uh, Thus, the mobility will increase with the increase in the temperature in this region, right? It was straightforward, this one. Is this clear, or does anyone need further clarification on this one? Just let me know in the chat, or just type next and I'll move to the next question. Fine. So let's uh, attempt now the question fifth. Molybdenum crystallizes in a body-centered cubic structure with lattice constant A given by 3.147 angstrom. If the 1 point radius of molybdenum atom is one half of the center to center spacing of the nearest neighbors, you need to compute the percent of the cubic volume, A cube, that is occupied by the molybdenum atoms. Just try this out. Is it 50%? Should it be 32%? Should it be 68%? Should it be 78%? Okay, how will you approach this question? See, if any one of you would have unmuted yourself, the feedback would have been a real time one, right? I would have been able to understand your thought process and accordingly tune that. Fine. Let me give a hint. Okay, this I expect all of you to answer. This is cube, okay? Take it as a cube. Fine. We have two diagonals, right? One diagonal is this one, right? In this plane. Fine. If this is A, what should this be? First of all, what is this diagonal called? There are two types of diagonals in a cube, right? This one is it's lying on the face of the cube, right? So this diagonal is face diagonal, right? This one is face diagonal. Cube has, I mean, all the edges in a cube are A, right? So this one is A, this one is A, everything is A, right? So this is a right angle triangle. This is A, this is A. So what should this be? Assume this is 90 degree, okay? What should this be? Root 2A, correct. This would be square root of A square plus A square, which is, I mean, square root of 2. I mean, A I'm taking out, okay? A root 2, which is what Shailendra wrote. Okay, so this is your phase diagonal, right? Let me write this. This was your phase diagonal. Phase diagonal is root 2A. In fact, let's do one thing. What happened? It's not fine. Phase diagonal is root 2A. Okay. I'm using color scheme so that we are able to track all the genes. Then there is another diagonal, right? Which side should I use? Okay, I'll use this one. From this corner to this corner, right? Imagine a line. Are you able to imagine this line? This is which diagonal? As I mentioned before, there are two types of diagonals, right? The first one is the phase diagonal, which we worked out as root 2A. This, the one that I draw with red line. This one is called body diagonal, right? And it's equal to, hint is you need to use the phase diagonal to compute what is your body diagonal. Okay, let me help you out again. So to compute this, use this right triangle, right? This one, and this one. This is A. This is root 2A. So what should this be? Root 3A, correct. And this diagonal was body diagonal, right? So this is your body diagonal, root 3A, right? Now, what is our center to center nearest neighbor distance, right? Center to center nearest neighbor distance, I mean this distance, right? This is this point to this point, right? This distance is half of the body diagonal, right? It's along the body. Imagine this along the body, right? So this distance would be half of the body diagonal, right? So let me just write this. This is our center to center nearest neighbor. That is equals to root 3A by 2. Fine. Now, just a second. Just give me a second, okay? Now, we computed the center to center nearest neighbor distance, right? Now, what is the radius equal to? What should the radius be equal to? Radius should be half of that, right? Radius would be root 3 by 2a whole divided by 2, which is root 3a by 4. Is this clear? Now, what is volume then? Volume is given by 4 by 3 for a sphere, right? 4 by 3 pi r cube. You all know this formula, right? So this is 4 pi by 3. That is where this mic would have been handy in order to, I mean, type the answer in the chat. It will take long time, right? On the other hand, if you would have a mic, pen and paper, you could have worked it out and just let me know the answer. Please make sure that you have access to mic from next session onwards. Okay, that would really make the session more interactive. So this is 4 pi by 3 r cube, right? And r is your root 3a by 4 cube, obviously. If you work this out, this would come out as pi by 16 root 3a cube. Okay, simple. Then we have what is the total volume? So the total volume would be twice of this, right? Let me just write this. Our total volume. Oh, damn. Just a second. Our total volume would be equal to uh, why 2 times? Anyone? 2 times this. Okay. Yeah, correct answer. Because for BCC, since it's BCC, that is why this, I mean, we are using this. Wait a second, why I'm not able to paste this? I should have been able to copy it first. Just write it out. This is pi by 16 root 3 a cube, right? So this would be pi by 8 root 3 a cube. Is this clear? So now what would be the volume of the cube occupied, right? Percentage volume of the cube that is occupied. What would be that? Anyone? Pretty simple, right? You need to divide this total volume by volume of the cube, right? Let me just write it first. This would be percentage volume of cube occupied, right? That would be equal to this total volume that we computed, right? Whole divided by A cube into 100. Right. So what would this be? Let's try to fit this in this page itself, right? Let's not waste another page. This would be pi over 8 root 3 times 100, right? Work this out. This should come out as 68.01%, right? So that's why the option that we'll go with is this one, right? Now this one is easy and I expect majority of you to attempt this. So which band will result in the heavier electron effective mass, right? In the lectures, I mean, the professor taught about the concept of effective mass and how is it related to the band curvature, right? So you should be able to solve this one. Pretty simple question, but a conceptual one. Please attempt this. No one? You need to answer. I mean, there are, this is sort of a binary question, right? Either A or B. Which one? A or B? Which one has the heavier electron effective mass? Anyone? Okay. I expected at least some of you to solve this one. See, effective mass, what is effective mass by definition, right? It is h bar square by dou 2e by dou k square. So effective mass is inversely proportional to the square of this. If inversely proportional to the band curvature, right? That is what effective mass in essence is. So the curve for which the band curvature is greater will have the less effective mass, right? It's inversely proportional. So since we'll write it in this way, since dou 2e by dou k square A is greater than dou 2e by dou k square B, right? Since A has more curvature than B, thus m star A would be less than m star B, right? This is your answer. Is this clear? Why band A will have, I mean, lighter electron effective mass and band B will have the heavier electron effective mass? I hope it is. I'll move forward. The next one is pretty straightforward. The question is, what among the following is a Brillouin zone by definition? Should it be A, B, C, or D? See, firstly, we can reject some options clearly, right? For example, this is position space, right? Region of position space. This cannot be Brillouin zone. Energy space, no, it's not that. Another name for a unit cell of the crystal, no, it's not a unit cell of the crystal. Then what are we left with? Option A, yeah, right. So has to be this one. In fact, Brillouin zone, it is a set of points in the K space that contain all the unique solutions of the wave equation. Okay, so that is what Brillouin zone is by definition. You might have seen this, right? Extended representation of the Brillouin zone and reduced representation, right? This is the extended one. This is the reduced representation. You would have seen both of these representations in, what should I say, the lectures that were taught by professor. So yeah, we'll move ahead. Now to the question 8, which is consider a semiconductor whose energy dispersion relation E of k for conduction band is defined by E is equals to A plus B times K minus C whole square, right? Where your A, B, and C are constants. You need to assume that the mobility of the electron is mu naught. You need to find the mean free time of electrons in the conduction band. It is actually a simple one. Anyone who would like to attempt this? Since this is a straightforward one, I'll just wait for a minute just in case any one of you is able to do it yourself. Hint is you'll start with, let me drop a hint. You'll start with the relation of the m star, how m star, I mean, is a function of E of k, right? How is it related to the EK relation? Then you'll use uh, mu naught. What is the expression of mu naught in terms of mean free time, right? Which is nothing but q tau by m star. You'll plug m star here. You know mu naught. Compute this. This is how you'll get mean free time. I just told you the recipe. Let me see if anyone is able to work it out. I'll just wait for a minute. Okay, so I guess, okay, so you mean C, right? Let me see. Is it C? Mu naught h bar square by 2 qb. Yes, correct. It is C. So how did we obtain this? Let me just quickly now write what I just briefly described, right? Your E was A plus B times K minus C squared, right? So your what should I say? Your dou dou by dou k, right? Your dou by dou k would be 2 times b times k minus c, right? And then your dou to e by dou k squared, that would be 2b, right? So, and we know that this m star is h bar square by this dou to e by dou k squared. So this is h bar square by 2b. We know now the effective mass. What about this expression that I just told you? Mu naught is q tau by m star. So what should be tau? Tau should be m star mu naught by q, right? What is the expression for m star? We'll plug this expression right here to get tau. So this is what we'll obtain. Our tau would be equal to h bar square by 2b q mu naught, which is what Shailendra said, right? Option C. So this is a correct one. Is this clear? I hope it is. I'll move forward. Okay. Now the next one, an easy one. In chronic penny model for a 1D crystal, you need to choose the envelope that best fits the E versus K plot, right? Note that this envelope doesn't model the forbidden energy. Your A is some arbitrary constant. Okay. Just check if you can finish this one. This is actually pretty straightforward. Anyone? You all saw that parabolic relation, right? In terms of k square, right? I mean, we are, uh, ignoring the forbidden energies because we don't need to model them. Apart from that, this portion is modeled by this expression here, right? This is actually self-explanatory, right? It's a parabolic expression. So I won't go into the details. So now the next one, right? Let's say an oscillator for microwave generation is to be designed for motion detection, right? So what type of semiconductor material would be most appropriate for this? Would it be gallium nitride? Would it be silicon carbide? Would it be gallium arsenide? Or would it be none of the above? Would be some other material? Please suggest if you have some other material in your mind. Anyone? Okay, I guess I'll write it myself. So the correct answer is gallium arsenide. Why? The reason is, let me just write it out for you. Your gallium arsenide is best suitable because its higher mobility results in lower excess resistance and accelerates the channel electrons, right? Accelerates the channel electrons to their saturated velocity, which rapidly, it accelerates the channel electrons to their saturated velocity rapidly over a short distance. So there, right? So that is the reason uh, we choose gallium arsenide for this application. Okay. Now the next one, again, a straightforward question wherein you need to use this effective mass m star expression again, which we used, I guess, for a couple of questions before, right? If E of k is given by 2 sine square k, what is the expression for effective mass m star? Please, all of you attempt it. Try to solve it on paper and let me know if it's A, B, or C, or none of the above. You work it out. And I'll be taking a 3 minutes break, right? In these 3 minutes, try to work it out and just type in which of the options is correct. Okay, just do it and wait. I'll be back by 3 minutes. All right. Were you able to solve this one? Okay, somebody is saying it's h square by 4 cos 4k. Is it? Okay, maybe there is a typo in the options. Let's work it out. Okay, let's work this one out. would take much time. So it's m star, that is equals to h bar square by dou 2e by dou k square, right? And what is our dou 2? Wait, what is dou e by dou k? Dou e by dou k. Wait, I'll actually solve it quicker. If we write e of k is equals to 2 sine square k, right? So this is 1 minus cos of 2k, right? And what is now, if I differentiate this twice with respect to k, just work it out, it should be 4 cos of 2k. So yeah, I guess it's not matching with the options at least. So what should be m star now? M star should be equal to your h bar square whole divided by 4 cos of 2k. Okay, this is your answer. Is it fine? Okay. Actually, Stephen had already written, I mean, mostly right. Just that the argument of this cos would be 2k, right? It won't be 4k. It would be cos of 2k. Otherwise, his answer was correct, assuming he meant h bar by his h. Okay, now let's move ahead. Okay, what is Wigner-Seitz cell of FCC, obviously? First of all, what is Wigner-Seitz cell? It's special type of a primitive cell, right? I mean, it is a cell of a lattice point. The Wigner cell of a lattice point is defined as the volume that encloses all the points in space which are closer to this particular lattice point than to any other. Okay, so uh, if I talk about the 2D construction, right? If I talk about the 2D construction, then one chooses any lattice point, right? And if one draws the connecting lines to its closest neighbors, you already have read about this. I'm just recapitulating this. In the second step, one then constructs a perpendicular bisectors of connecting lines, and the enclosed area is what we have for the Wigner-Seitz cell. So just remember, Wigner-Seitz cell for your FCC's lattice is uh, this rhombic dodecahedron. Okay, this one. So this is how it looks, right? This is how it looks. Fine. Let's move ahead. Now we come to this one, question number 13. Okay, so which of the following statements explains the relevance of effective mass being negative for some particles in solid state physics? Again, this is a simple one. So which of the following statements, explains the relevance of effective mass being negative for some particles? Well, let's see first option, right? The effective mass being negative indicates that the particle's behavior is unconventional and deviates from the standard free particle models. Well, I mean, it is unconventional, but this is not appropriate, right? This is not appropriate. We won't go with this one. What about the second one? The phenomenon of this negative effective mass. It is still a subject of ongoing research and its complete implications are yet to be understood, which is wrong. We know what negative effective mass is and we do know what are its implications. So first two are, rejected. The third one is negative effective mass. It implies that the particle experiences an attractive force towards the region of higher potential, leading to a unique electron behavior. Well, this does make sense. In fact, option 3 is what is correct. What is option 4? Particles with negative effective mass, they are more stable and have higher conductivity compared to the particles with positive effective mass. No, we'll go with this one, third, right? Let me add a brief, I would say, an explanation. So your effective mass, it emerges as a result of expanding energy dispersion near its, what should I say, minimum, maximum, where it's, I would say, correspondingly positive, negative, right? Positive, negative. So in the latter case, particle, what kind of force does the particle experience when the effective mass is negative? Please write that in chat. In the latter case, particle experiences an attractive force, right? Because effective mass is negative towards the region of higher potential. Now, this is today's last question. I mean, this turned out to be a pretty brief session than I expected because, see, unless you guys will interact, these sessions will be very short. So the only, see, the time slot is of 2 hours, right? So the reason is, I mean, it's expected that you guys will interact and your interactions will, I mean, obviously solve your doubts and all, but they will take up some time, right? But since you guys are not interacting, these sessions will, I mean, finish pretty quickly. I guess good for me. So yeah, now let's see what question 14 says. When a crystal is subjected to monochromatic X-ray beam, the first diffraction is observed at an angle of 10 degree. Okay. Okay. So you need to determine the angle for the third diffraction when the same X-ray beam is used. You need to mention the answer in degrees. Please attempt it. This is today's last question. Let's all, I mean, at least make an intention of attempting it. Please do that. Okay, let me help you out with the approach. And I'm sure meanwhile you'll work it out at your ends as well. So see, this is what is given. It's actually a very pretty straightforward solution. See, for n equal to 1 theta 1, it's 10 degrees, right? It has been given. Now, what is, we'll have this, right? 2D sine of theta would be equal to n lambda relation, right? We have this relation. And for first order diffraction, I guess I should write this as well. For first order diffraction, for first order diffraction, what we'll have? We'll have 2D sine of theta 1. Our n would be 1, right? So it would be lambda. So what do we get from here? From here, we get that this lambda by, wait, I guess I should write in this line as well. So this relation actually gives us lambda by d is equal to 2 times sine of 10 degrees, right? And what is this 2 times sine of 10 degrees? This would actually, I mean, verify for me if you guys actually have a calculator in front of you, right? Just work it out. What is 2 times sine of 10 degrees? Okay. I'm happy at least one student answered it. So it's not as if nobody has calculator in front of it. Okay, two students answered it. Good, good, good. So I would again make a request to all of you from next session onwards, have a calculator in front of you, have notebook, have a pen and solve with me. Only then will this session be an interactive one. Fine. So as these guys, I mean the two students pointed out, it turns out it is, right, it is 0.3473. Okay. So let me write for third order diffraction, 2D sine of theta 3. That would be equal to n times lambda. N would be 3. So it is 3 lambda, right? So what would be theta 3 then? Wait, theta 3 would be sine inverse of this 3 by 2 into lambda by d. Isn't it, right? Just mathematical jugglery. So just work it out, put the values, right? You know this, right? Lambda by d, you already know, right? Put that here, compute the sine inverse of that and report me theta 3. Report it in degrees, right? Because we have been asked that you need to mention the answer in degrees, right? So we'll solve it in degrees. So I'm expecting again two answers because I'm assuming two students do have the calculator in front of them. 31.39. Okay, I'll take that. Okay, the other student, do you agree with him? Are you also getting the same answer? Fine. So both of them got this, so I'll go with them. So this is 31.39 degrees, right? So this is what is answer, right? So we had to compute this, right? Angle for the third diffraction, and we computed it. So this is our theta 3, that is 31.39 degrees. Done. Fine. So in fact, that finishes this session itself, right? So does anyone have any doubt, I mean, with respect to the questions that we did today? If not, then I have a small clarification, right? Uh, Wait, I guess I should I'll in fact add a timestamp in the YouTube video of clarification uh, from this point. Reason being, uh, in week one, although we had solved this question number 9 correctly, right? But we just made some typos here. This was a square, this was a square max, this was a square min, right? And is it? Yeah, that was pretty much fine. So these were the mistakes that I had made. I mean, I took this square in my mind, but I just forgot to write them here, right? So I'll in fact update the slides as well. So please check the updated week 1 slides as well. They'll have these corrections, okay? These 3 corrections. Rest is pretty much fine. Yeah. I don't have any other clarification with regards to week 1, and week 2 is already done. So anyone has, if anyone has any query, please go ahead. Uh, Otherwise, we can just end the session right here. Okay, there was one student who mailed me that question number 456 of week 1 assignment that requires content that was not taught in week 1. Is that the case where you guys able to solve question number 4, 5, and 6? I asked him to post this query on the forum, but uh, I guess he did not get the response. So that's why I'm raising it here. Can anyone just at least verify if he or she was able to solve the question number 4, 5, and 6 of week 1 assignment, which is due on 8th of August? An acknowledgement would suffice. Anyone? Okay, fine. If no one has any other query, okay, somebody is typing, I guess I will wait. Fourth question was taught last Sunday by you, sir. Oh, is that the case? I mean, if I taught that, then I mean, I might have taught a similar question, but the point is, I only taught from the content that was taught in the week 1 lectures, right? So I'll assume the student that asked me this question will need to see the lectures again. And once he does that, he should be able to solve this fourth question. And were you able to solve all the questions? I mean, you attempted all the questions, right, Shailendra? I need hint for first question, sir. First question, wait then. I would really be happy if anyone in this meeting would go ahead and drop a hint for question number 1. Just don't reveal the whole question. Just drop a hint. I need to check what the question was first before I could drop myself a hint. Where is the question? Where is the question? This one is not. Um, hmm. Just a second. C24 EE-143. Why am I not able to open this? It should have been enabled. Okay, if I sign out. Uh, uh, mm, okay, it's week 1, right? Let me see. Week 1, assignment 1. Okay, for a given wave function psi of x that is given by max of modulus of x minus pi, a max of this function and k times 1 plus cos of x. When mod of x when mod of x is less or equal to beta, and it's equal to 0 when this modulus of x is what should I say, greater or equal to beta, right? What is the value of the beta so that this wave function is valid? Okay, so firstly what you should do is just plot this psi of x. See, I'll just give a vague hint because the moment I'll go deep into the question, it would just reveal the details of this question. So I'll just drop a vague hint, right? Psi of x, you need to just first plot this psi of x, right? Then the value of the beta so that the wave function is valid, right? The computing that value of beta you would get when the psi of x would be continuous, right? So that is all I can say. The rest, I guess you are too smart to understand. Is that fine? Okay, fine. Thank you. Uh, that was his query. Anyone else who has a query? Because if not, then I'll wrap this session actually. I guess that's all right. So we'll be ending this session right here. Thanks a lot for tuning in. I'll see you guys next week, Sunday at 5 p.m. Okay, bye. Have a good day.